Hello students, in this video we'll consider the wave equation on a disk. The wave equation has the form UTT is equal to UXX plus UYY. The region we're going to consider is x squared plus y squared less than or equal to 1. I'm going to assume that when we're on the circle itself, so when I restrict u at any time, so u restricted it to the circle, restricted to the set x squared plus y squared is equal to 1 at any time t. So in other words, if I plug in the values of x squared and y squared that give me a point on the circle, it's going to be equal to 0. So I imagine that what's happening over here is I have a membrane and it's attached to like a drum, for example, right? So in other words, it's not moving at the boundary, and I'm going to put it into wave motion by some initial force, for example. Okay, that's a condition. That's my initial condition. That's my boundary condition over here. So our boundary condition. And of course, if there's some circular symmetry in the problem, if this is our domain, and we'll assume also that u of x, y, 0, and u of x, y, 0, t are known. So those are known boundary conditions. Those are going to be known to us as functions g of f of xy and g of xy. Okay, so this is our setup for the wave equation on this circular region. And so of course what we have over here is we can imagine that I have a membrane over here. So I'm just going to draw this with some perspective. If you think of like a drum, for example, what I have over here is I have a circle in space, right? And what I'm going to do is I'm going to basically strike the drum, and it's going to undergo wave motion, right? So I'm going to have some wave-like motion on this, but of course it's going to be fixed to the edge of the drum, right? So the edge is not going to move, the boundary is not going to move, but the interior membrane is going to move, and we're going to model it with the wave equation. Great. And so of course the key idea behind this is we're going to put this into polar coordinates, right? So let's recall that uxx plus uyy, we've proven this in previous videos, is really urr plus 1 over r ur plus 1 over r squared u theta theta in polar coordinates. And so this equation really becomes what? Our PDE really becomes UTT is equal to URR plus 1 over r ur plus 1 over r squared u theta theta. And now, of course, r is between 0 and 1, and theta is between 0 and 2 pi, right? So now our situation, our domain changed a little bit. Our r is between 0 and 1. And theta is between 0 and 2 pi, right? So I've turned it into a rectangular region by looking in polar coordinates, okay? Now we're going to separate variables. So let's separate variables. We're going to assume that u of r, theta, and t is a function t of t, is a function r capital of r, and a function a capital of theta, right? And so now when we separate variables, when we plug it in, we're going to have what? We're going to have t double prime, and now I'm going to suppress the independent variables here. So I have t double prime times r times a is equal to r double prime times t times a plus 1 over r prime ta plus 1 over r squared, r, and then t, and then a double prime, right? So I divide by r, a, and t, right? We have t double prime over t is equal to r double prime plus 1 over r prime over r plus 1 over r squared plus 1 over r little r squared, a double prime over a, right? And so now I've separated the equation, and so what we're going to do is the following. So now we're going to use the common separation of variables technique. We're going to say that this thing over here, this negative, this t squared over t, so t double prime over t, has to be equal to some constant negative n squared, for example, right? Because this depends on t and this does not, so this has to be, so t double prime over t has to be some constant called negative n squared, right? And that gives us a differential equation for t that says that t double prime plus n squared t is equal to 0, like that. And then if that's the case, then we have what? Then I know that this over here, this depends on, this expression over here depends on r, this depends on theta over here, so that also has to be a constant. So we can also conclude that a double prime, so a double prime over a also has to be a constant, and that constant has to have the following form. Now, of course, the a has to be 2 pi periodic, so this has to be negative m squared, where m is an integer, right? And so this says that a double prime over here plus m squared a is equal to 0. Great. And so now, of course, what do we have? So now what's the R equation going to satisfy? So, of course, all of these things are going to give us trigonometric solutions over here, right? So those are very easy to solve. Those are going to give us trigonometric solutions, okay? And, of course, the reason why we want n to be, this negative n squared to be negative over here is because I need there to be bounded solutions to this. I don't want there to be an unbounded solutions in the time component, right? So the time profile can't be unbounded over there. Great. All right, so now let's continue. So now what does the R equation look like? The R equation looks like R double prime plus 1 over R prime over R, and then plus 1 over R squared, A double prime over A, we assume to be negative m squared. That's going to be a negative m squared. Negative m squared is equal to what? Is equal to negative n squared. Negative n squared, like that. Okay? Multiply by R, great. Now multiply by R squared and R to the equation, and what will we get? We're going to have R double prime, R squared, R double prime, plus an R prime, plus a what? Plus a negative m squared R, so I have a negative m squared R, and then a negative, then a positive n squared R squared will go on the other side, minus m squared times R is equal to 0. Like that. Great. Okay? So now I have to find solutions to this. Of course, when n is equal to 0, it's just going to give me when n is equal to 0, it's going to be a Cauchy-Euler equation, right? And the Cauchy-Euler equation will have a constant solution. And so we're going to consider the case when m is not equal to 0, right? When n is not equal to 0, okay? Because if n is equal to 0 over here, that's just going to give me a linear solution over here. Or since I can't have growth, that's going to be a constant solution. So when n is equal to 0, we just get a constant solution over here. Okay? So n not equal to 0, then what's the solution of this going to be? The solution of this is going to be Jm, the only bounded solution. This is, of course, Bessel's equation of order what? This is Bessel's equation of order m, right? For m an integer, with scaled by n, right? So as the only bounded solution is J what? Is Jm of nr, like that. Okay? Great. And so now, of course, we can say, and so the other solution, Ym of nr is unbounded at the origin. So now what we're going to get is the following. We're going to have solutions. So we need to satisfy what? We need to satisfy when I plug in any point r equals 1. So when r is equal to 1, I have to get 0, right? We also need that Jm of n is equal to 0, because that's when I plug in r equals 1, right? That, of course, corresponds to r equals 1. So that says that n has to be a root of Jm, right? So n is really lambda m for the order of the Bessel equation, and then k, where k goes between 1, 2, forever. So in other words, those are the roots of Jm. And we know there's infinitely many of them. Okay? So now we're in a great shape because I know that those have to correspond. So now I have my standard forms of solutions. So what's my general solution going to look like? My general pieces of the solution to this boundary value problem are going to be what? The solution pieces, the pieces, are going to have what form? Are going to have the form Jm of what? Of lambda mk times r. Those are the bounded pieces of the radial. Those are the radial solutions. Then we're going to have what? We're going to have some constants over here. So of course, what are the a solutions going to be? They're going to be cosine of m theta and sine of m theta. So I'm going to have a cosine of m theta times am plus bm times what? Times the sine of m theta, and then times what other functions over here, times the angular solutions, which are going to be what? Are going to be a cm, or cn, of course, cn cosine nt plus cn sine nt. Okay? And so now what I'm going to do, that's for any k, so I have to sum over m and k over here. So what are the values of n? Of course, these n's get replaced with what? So actually, we have to replace these n's with these lambdas over here. So let's replace those n's just to make it more clear what those n's really are. Those n's are really those root functions over here. So what we have is we have one more term in the product, which are what? Which are going to be a c and then mk cosine of lambda mkt plus dmk sine of lambda mk t, like that. So in other words, if I sum up these expressions over here over all values of m, so what will m be allowed to be? M is allowed to be anything between, okay, we have constants as well, right? So m can go from 0 to infinity, we have j, and then k can go from 1 to infinity. So if I sum up all these expressions from m going from 1 to infinity, and m going from 0 to infinity, and k going from 1 to infinity, so m goes from 1 to infinity, m goes from 0 to infinity, and k goes from 1 to infinity. By the way, I parameterized it. And if we sum up all those basic functions over here, then we'll get the solution. And now, of course, the next phase of this process over here is to be given f of r and theta and g of r and theta. And then what I can do now is I can differentiate this with respect to t. I can then fill in and find the Fourier-Bessel coefficients and then plug in f of r of t into this when t is equal to 0, and we get only these CMT terms over here. And so I have all of these. I have an infinite number of solutions to this wave equation, right? Parameterized by m and parameterized by k. So I have two indices, and if I sum over all m and all k of these functions over here, plug in the initial conditions, that will allow me to solve the wave equation on this disk reason using the method of separation of variables and employing tools from the theory of Bessel functions, namely that Bessel functions of any order, of any integer order, have an infinite number of roots, and they satisfy an orthogonality relationship, which will allow us to compute these coefficients in this series using those orthogonality relationships and the Lommel integral formulas. Thank you very much.